Okay, so now that this short video is for the scalar or dot product of two vectors. Okay, now as we learned before, the dot product of two vectors, mainly if you were to look at a vector in a three-dimensional format, this is a1, a2, and a3, and the vector b is consists of the components b1, b2, and b3. Now the scalar or dot product of these two vectors will be equals to a1, b1 multiplied with a2b2 plus a3b3, right? So it's a1b1 plus a2b2 plus a3b3. Okay, so eventually if you take a look at, for example, let's look at maybe just look at, for example, if a is equals to 1 2 3 and b is equals to 4 5 6, then the scalar product or dot product of a and b will just be equals to 1 2 3 scalar product with 4 5 6, which will just give you 1 times 4 adding with 2 and 5, so a2 b2 adding with 3 and 6, a3 b3, which is 4 plus 10 plus 18 to give you 32, right? This is an example of the teaching of the scalar product. So let's look at one example over here. Alright, so a equals to 1 1 negative 1, b equals to 1 1 1, c equals to negative 1 negative 1. Right, so I'm just going to show you part A first. So part A, what's the scalar product A and B? So A and B, you just have 1 1 negative 1. This is part A. Scalar product with B is 1 1 1. So it's just 1 times 1, you have 1. 1 and 1 again. It means 1 and 1. You have a 1, negative 1, minus 1. So total is 2 minus 1, you get 1. So the answer here is 1. Alright. And for B, similarly, B will be a scalar product of B multiplied with A. And you will also get a 1 plus 1 minus 1, which is 1. So one thing interesting you can notice is that the dot product of A and B is the same as the dot product of B and A. So if you want from A and B, right, you can actually deduce, inference one result as a scalar product of A and B. It's the same as a scalar product of B and A. Alright. So let's think about, maybe pause this video now. Take about 5 minutes. Let's just try to do the rest of the examples on your own, okay, before you go to the next slide. Okay, so after trying the examples, you can actually check your answers. If all goes well, A dot product with B plus C, this just means that out of operation, I will actually do the addition of B and C first, which is 1 1 1 plus negative 1 negative 1. And this will give me a 0 2 negative 1. And I do the scalar product. So this is my A, and this is the B plus C. Alright, and after that I get answer 2. Right, for A dot B plus A dot C, then this will come first, and then followed by me adding them together. A dot B from part A is just 1. So we combine this, negative 1. There's some presentation error here. It should be negative 1. Okay, so the answer will be 2. So you realize that actually, in general, if you look at compare C and D, right, you just compare C and D, you realize that it in some way it resembles the distributive law of just a normal. So it's like if we have this in algebra, right, you will call this in algebra. You still this before secondary 1, if you expand factorize form, you can actually get so it's something similar in vectors. So this similar in vectors is the vector product of A, the dot product of B plus C, dot vector product is equals to dot product A and C plus dot product of B and C. Okay, yeah. And same for E and F, you can just verify the answer. Alright, so next, what's the laws that you can generalize? Number one, A dot B is the same as B dot A. Okay, this is for part A and part B, as you can see. Okay, we call this the commutative law of scalar product. Part B, distributive law. Similar to algebra, A dot B plus C equals to A dot B plus A dot C. And all these are important when you're doing your question, so do remember. B plus C dot A equals to B dot A plus C dot A. And you can see that these two, right, are the same based on part A, right? And these two also the same based on part A. And how about A dot lambda B? A dot lambda B, if you can observe part E and F, suppose the 2 here is our lambda. It's like A dot lambda B, right? Can you see that this is the same as lambda A dot B? So part E and part F actually give you the same answer. From here you can also generalize the conclusion, right? There's a A dot lambda B is also equals to lambda A dot B, right? So with that, if you observe this third, that's what we call associative. So remember that lambda is not a vector. So lambda is just a scalar, just like a factor. So if it's just a factor, we can throw it outside. You can put it outside and we do our dot product first before we bring in the scalar. Right? We call this associative law of scalar product. So just remember that for scalar product you have commutative, distributive as well as associative law. Last but not least, if you look at the last example, right, A dot A, right, is A1 square plus A2 square plus A3 square by virtue of the operation of scalar product. You can see actually in a way this looks like the modulus of A square, right? So what's the modulus of A square? So if we look at the negative of A square, so if we look at this, right, modulus of A, this is equals to like A1 square plus A2 square plus A3 square, correct? So if we were to square this, it's as though we are squaring this, right? Now the square and the square root, they cancel out. So we end up with A1 square plus A2 square plus A3 square, which looks exactly like our scalar product, right? It looks exactly like our scalar product, right? So that's how we get this conclusion. That's how we get this conclusion that actually the square of the magnitude is the same as the scalar product upon itself, right? Okay, that done for scalar product.